Dhananjay is an electronics grad from Pilani, Goa. One of the co-developer of Robo Earth project, which he built as a part of his bachelor's thesis at Swiss Federal Institute of Technology, Zurich. He has been developing in Python for 6 years and worked with Samba over the course of 2 summers, summer of code projects as an avid open source enthusiast. He also contributes to a bunch of projects such as Genome and Samba. In his off time, he enjoys traveling, loves the outdoors, and is a self-described administrative junkie. Thank you. Please welcome Dhananjay.
Yeah, good evening. So today I'll be talking about Rapayuta, or the Robo Earth Cloud Engine. As the name suggests, building castles in the sky. The name is inspired by a Japanese movie called Lapayuta, which means exactly that. Here's a shameless announcement about me. You could reach me on any of the social networks or GitHub and get in touch. So starting off, how many of you have heard of cloud robotics? Okay, most of us here probably have heard of cloud computing and robotics in 2 different domains. So something interesting happened at Google I/O in 2010. The entire concept of cloud robotics was introduced by James Kufner, and a lot of work has been done by Eugen Robotics and Willow Garage on this. So what's the difference between human beings and robots today? Is human beings learn from each other. When you have a doubt, you head up to Wikipedia or head up to Google, and you look up what you want, and you learn from your environment, and you learn from each other. Most robotics projects today don't do this. They start reinventing the wheel, reteaching everything from the scratch. What if robots had a common method to communicate, to learn from each other autonomously? It would be a completely different game. Some basic examples of cloud robotics in use today is the driverless car by Google, and these automation robots by Kiva Systems that's used in Amazon warehouses. So what is the Robo Earth project? Under the European Union's FP7 framework, they set out to create an autonomous robotics platform, or a worldwide web of robots, called Robo Earth. And this involved a few basic components. So if I were to ask you, what would you need for a robotics platform to perform all the tasks that a normal human being or an intelligent system would perform? We would need 3 basic components, right? First is a language. How do you represent objects in the real world? It's far more complex than just mathematical if-else statements. What would I want to share, and how do I share it? What do I execute, and how do I execute it? And how do I reason, right? So there are projects that are going on in this field in various research labs in MIT, in CMU, at ETH, and other universities. But to give you a brief idea of exactly what we intend to do with this platform is this famous scene from The Matrix, where she does not know how to use that tank or the helicopter, and she downloads a program to do it. In the robot language, we call this an action recipe. It basically tells a robot how to perform a function, and the robot is self-aware enough, and it has enough introspection to figure out how it would evolve from a robotic arm to a full-fledged PR2 or a simple Roomba robot. So this is some basic stuff that you use, and it's called an action recipe. Naturally, the next component you would require would be storage. How do you store a million different things? I mean, this Wi-Fi router or this projector, we could look at it and tell what it is. It's a projector, it's some kind of a switch. How do you do that for a robot? One major step forward is the Google object recognition engine that they've provided and people use commonly in open source. So our server is based on Hadoop HDFS, so it's quite scalable. And we use a SysAM server and a Serial server to provide the semantic context of how do you store your schemas in the Cloud Engine libraries. And the third component, which I will be concentrating on today, is the computation part. So the computation actually finally makes sense of whatever data you have, whatever raw signals and impulses you have, and tries to put it all together. So this is a basic layout of the Cloud Engine, where you have the Cloud Engine in the middle, and all your standard databases. It could be sources, it could be APIs from Google or whatever else, and then you have clients. So let's look at one of the things we presented at Roscon this year at Stuttgart, is a turtle bot. You have a basic turtle bot, which is built on a Roomba robot, a Asus XT Ion Pro, which costs $200, and so the total cost was around $250, and the task was to do real-time 3D mapping of our lab in ET at Zurich with Amazon EC2 instances, HVM instances based in Ireland. So this is a video that briefly explains it. Do I have audio? So I'll explain it, so it's okay. So this is just explaining what I did. So we take our robo over here, and it's in our own facility. And the robo view is all this goes all the way to the cloud in Ireland and comes back. And we're generating keyframe points over here, which is basically a point cloud. And we're using CCNY RGBD SLAM algorithms on the cloud. And as you move around, you can see the real-time map being generated in 3D. And you can browse into it. So the applications will be potentially, if you've seen those juggling quadcopters on TED by Professor Raffaello D'Andrea in our lab, so we could probably hook them up and generate 3D maps and do really cool stuff, even with really low-cost equipment and stuff like that. And that's actually a really good map and you could use further algorithms on it. Oh, shit. So I'm going to explain briefly what the infrastructure and the architecture of the entire cloud is. We have a single master node, which is basically responsible for incoming authentication, user management, control other components, set up interfaces between various nodes in the cloud, and some other basic stuff. Then in every node, you could have a computing node, which is essentially a container process, as we call it. It's run in super user privileges mode. And it's used to set up computing environments within a physical or a virtual instance on the cloud. And we use LXC containers, similar to Docker or Flynn, or even Heroku for that matter. And these form building blocks for computation in the cloud. The next process that we have is a robot process. This is like the robot overlord. It controls and handles connections between the cloud framework and other parts inside the cloud. And there are different protocols to it. I'll come to the communication part in a bit because it's highly specific and important. The computing environment, as I said, is lightweight LXCs. It's a much better choice to KVM or any other mode of virtualization, as ideally most of your packages are in Linux, and LXCs start up in a much shorter time. They are much lighter, and they're much easier to configure. I can limit rates, I can limit usages. And inside each node runs an environment process that is responsible for all the connections and all the components as would be seen inside the brain of the robot. So essentially our robot and the brain resides in the cloud. And so what's going on here? This is a simple configuration where you have a master server and you have two nodes over here. And each server would have a bunch of Linux containers. Each Linux container would in end have an environment endpoint. And this is basically aimed to ROS, if you guys have heard of ROS. And it's a ROS node running inside it, which is a really large repository of robotics projects that is also an open source by the Robotics Foundation. And you have RECOM. Now this RECOM connects to robots via standard RFC WebSocket protocols. So the robot could be in anything. So the beauty about this is the robot could be designed in whatever language you like. You could design a browser app on your mobile phone using Automan JavaScript to talk to the cloud engine. And you could come up with a whole new schema or whatever you want to do. So, and you could have multiple nodes, multiple container tasks running multiple containers. So you could potentially run multiple processes in each host. The other side is a robot endpoint process. This does not reside inside the container. This is basically a converter. And we've coupled it really loose. So you could use your own converters. Say you want to handle RGBD data separately. You want to handle impulse data separately. You could use WebSockets to connect outside. Internal communication happens via RPC and custom protocols, or even MPI or some other scripts. And Again, this could be across machines. And this is putting together the whole thing, where you have your containers and your robot processes and your machines running across the cloud framework. And these little lines that you see are what you define. You need not define all ROS topics. Say I have a total bot, I have X, Y, Z velocities. I want to just show the Z velocity. Then I could just expose that and use that in my cloud as I wish to use it. So this was the part I was talking about, communication. So what we've done is it's a very distributed framework. So the master talks to all the nodes which are running the container task set or the robot processes using perspective broker based RPCs. So they are very small messages or control signals that are sent out and confirmations that we get back for just controlling the cloud. Any task between two containers or between two processes that are intensive use custom RPCs. Now these RPC channels are set up by the master using control signals. But data-intensive transfers are independent of master, so they do not depend on it. And even if the master goes down, the processes will not be halted or stopped in any way. The external communication, what we have chosen to use is standard WebSockets. We had to modify WebSockets for higher data rates, like 90 Mbps for the 3D mapping project that we did, and involve like asynchronous nature of 4G communications into it. But most of these changes have gone mainline into Autobahn Python, so we're using standard Autobahn WebSockets now. Yeah, the building blocks it's almost built entirely in Python. We use the twisted perspective broker for the groups, the authorization, the control signals, RPC for data-intensive tasks. Right now we're using custom code to provision and set up and control the LXE, scaling the configurations of Ethernet ports on the LXEs. And at some point, we'll probably look at the Docker and the Flynn projects if they mature enough to be used for such use cases. You could build apps in C, C++, Java, whatever you like, so long as it's compatible with ROS, it will work, right? Yeah, so today everybody is talking about apps, right? Your phone is basically a cloud-enabled device, and you have apps that run on the cloud and you interface with. So the cloud engine proposes an ideal future where you have such things. And we've so far supporting ROS distributions of Fute and Groovy. And again, it's completely standard ROS code. All you need to do is join the dots. It's like completing that map that I showed you earlier in step 5. You just need to write a JSON file that describes which interface you would connect to which socket, and so on. And you could use groups. We've introduced a new concept of grouped tasks. So what you need to do is define two robots in the same group process, and it'll spawn an automated VPC style connection where right now we use GRE tunnels. Linux 3.9 introduces VXLAN in mainline, so you could move to VXLAN, and potentially what this does is you could run GraphLab or other MPI-based high-performance tools, or it would be much more secure, and there are benefits. You could mount Hadoop file systems into it and run congregated MapReduce jobs, which would enable crazy stuff. We don't know what it would. We need to figure that out. So why Robo Earth? I mean, you could write a web app, right? You could write a web app to do a particular task. Why would you need an entire cloud framework for it? The major things is right now the whole framework is in open source, right? And it's more of a PaaS, SaaS border kind of use case. And you can take this and you can develop it as you want. You could swap out basic components. The code is completely documented. We have an active wiki. It's secure, it's open source. And one major thing for people who've actually worked on robotics would be that if you're using small robots with ARM processors, there are a lot of limitations that you run into. Now, what you can do by cloud robotics is essentially remove these limitations. I could use as the thing showed, you could use a simple ARM processor and use full AVXI instruction sets in x64, or use CUDA or OpenAI or whatever you wanted on the cloud, thereby removing these brackets that we had earlier. It's also being actively developed, and it's quite scalable for now. We plan to introduce a few more things. It's really easy to set up. When I joined the project, it was about 60 or 70 lines to set it up, and it was really hard to even get a basic instance running. Now it's a fire and forget script. It's probably as easy as setting up, I don't know, VLC. We also provide a public AMI that you could just look up and you could try it out on EC2 on your free 750 hours a year and play around with it. You could set it up on your own infrastructure. We've tested it on EC2, we've tested on Rackspace, we've tested on the Google Compute Engine and on our own commodity hardware too. So it works in all those places. And it has like a simpler thing. So if it detects you're using EC2, it has optimizations for it, auto configurations for it, and so on. So as people start using more platforms, we'll add those things in. An ideal use case would be, for now, you would have one master node with a ROS core instance running on it. You would have multiple robot nodes, which would be a robot process. You could spawn as many as you liked. You could spawn multiple nodes for computing environments. It's completely up to you. And config files for, as I defined, so it's very malleable. We've purposely not tied it into any infrastructure vendor or any base specification, so that because we want it to be as usable. At this stage, you cannot deploy custom code like you can git push onto Heroku. But what we do and what we are trying to figure out right now is how you would do that. But the decision that we took at ROSCON was not to allow individual deployments, but to have a public cloud, because the nature of the ROS community is so fragile right now and it's kind of new. So we want as many people giving back to the open community. You could very well take it into your organization and close it up. It's up to you, but it's always good to give back. This is a call for you guys to get involved. We have an active mailing list where you could shoot us any bug, and rest assured we'll come back to you quite soon. Focus on GitHub and contribute back. We're always open for more people coming in, and yeah, just generally. And if you're interested, if you're a student specifically, you could go to ETH. It's probably one of the best labs for autonomous robotics on the planet. You have all those flying copters to play with. It's a lot of fun, so I think you should get involved. And that's about it. Any questions?
Your talk was pretty cool. Thanks for that. What are some of the most practical use cases currently?
Currently, what we have done, sadly I don't have, the internet's not working, but what we've done lately is we've got multiple robots mapping in the cloud. Potentially, as you see the Internet of Things evolving and you move on to the whole IPv6 connected future, you would have everything providing data. Say you had a bunch of sensors in your subway, and this would be fed back into the cloud system, which is driving your trains autonomously. Then you would use this kind of data, or say you want to remotely map, say you want to colonize Mars, which is to be done on the human list. You would go there and you would need an autonomous system that takes care, it learns from itself. I mean, a human controller cannot go and keep typing and say, hey, what's happening, and there'll be a lot of delay between how people communicate from here to there. So these could be potential use cases for it.
What about the current use cases? Are there any?
Sorry?
Are there any people really using it in the field?
So really not right now. We would like more people to get it. We've actually just finally stabilized. We've been working for the last 6 months over it, and a lot of university research projects are using it. So that's where we're starting off with. Yeah. Yeah, so technology is going to grow, and any technology that's had impact on us and lately has always had positive and negative sides. And it's up to you to how you choose to see it. And to be very honest, I wouldn't be bothered about that right now, because these systems, the more you learn about them, you realize they're not. Terminator is not happening, not in the near future. Don't be even bothered by it. Huh? It should. I mean, it should, but Mechanics and battery technology is not yet there, probably. So, yeah. Yeah. So what happens is when the master node authenticates against it, similar to what OAuth does, you provide keys, and these keys are inserted into the process. Only these keys match. Do you have a secure connection? Of course, there could be a man in the middle or like that. So right now we're in a very experimental phase, but you could potentially improve your security over there. It's not really hard. It's very loosely coupled. It's open source, so it's up to you, right?
So you mentioned you're using a Hadoop engine to process semantics.
Sorry?
You're using a Hadoop engine, right? The analysis, and you're
Yep.
processing some semantics to to get robot to understand how they recognize the objects.
Yeah.
May I know in detail, basically, what are the semantics you are processing and how it's doing it?
So essentially, what we have on top is a Serial and an OWL database. And when you get a request, it has a parameter with it. Like you have different contexts for objects, different contexts for actions, different contexts for say some communication, different contexts for how I store data. And depending on that, you store data into the database. And what we've not figured out is how you're going to use that data yet. But it could potentially, it's up to you again. So it's very loosely coupled. It depends on your use case. So experiment was done in Eindhoven, where they used a arm from KUKA Robotics to open a door, and they stored those action recipe data. They moved it to a completely different robo, a PR2, and it went the other way. So a PR2 is a robo that has eyes and vision and a lot of sensors, and it's extremely expensive, and it can use that. A KUKA robot is essentially a robot that does not have eyes, it doesn't have anything. So it learnt from this, and it learned how to open a door. They were used in simulated medical cases also in Eindhoven, so that also did work.
Oh, hi. So basically I want to ask is the cloud framework that you're using, is it based on some existing cloud framework or you have?
No, that's what we are actually building it ground up.
Okay.
The entire cloud framework is what you deploy on commodity hardware. Of course, so this is not infrastructure as a service, right? You would need your infrastructure provider, and then you could layer it on top of this as a PaaS or an IaaS. So that's how it goes. Yeah.
Hello. So it's open source and everything, right?
Yeah.
So, so for example, I would like to contribute to it, but there's something like which comes to mind, like for me to contribute to such a project. It's like since anybody could take in, you can do it for good or for bad, right?
Yeah.
Like I see most of the technologies these days, like for example, your drones and all those things, right? I mean, how do you address that? Like for example, are you guys trying to address that, making sure that this open source technology is not?
So I personally believe the best way to keep something safe is to keep it open source. I mean, rather than evil corporation developing it, I rather develop it out in the open and let people see what's going on. Of course, it can be used. I mean, your mobile phones could be used to track you and kill you, yeah.
Yes.
Or internet could be used for hiring killers and
Exactly, yeah.
all sorts of content on /B. So it's up to you at the end of the day. You can't
I know
really
it's up
address
to you,
that.
but I mean, I want to hear from you since you're in the research field and you're actively contributing. So what, I mean.
At this stage, we aren't really taking processes. We don't think it's dangerous enough. So let's see how that goes.
I don't have any experience on robotics, or I don't have experience on artificial intelligence. I don't programmer. How do we contribute to such projects? What areas?
So
we should look into start?
The cloud engine, to develop it, you basically need basic knowledge of twisted, deferred asynchronous programming, because what we've done so far is we've made sure every part of the cloud framework is completely asynchronous and decoupled completely. So potentially if my robo runs into a building and stops sending impulses, it shouldn't block on some other process. So basically, it's a lot of perspective broker twisted. We're using LXE. We've been talking to a developer from Canonical who are working on LXE. And these LXE, the thing about LXE right now is it's quite good, but it's not completely secure. Because if you gain root access, you still have access to proc and sysfs from where you could do malicious stuff to your host system. So you could probably use gresec, and they are planning to introduce user space containers and user space devices. So even if you get root, you're still mapped to a different UID and a GID in the Linux kernel. So you still aren't root. So you would probably need some knowledge about LXE, mostly twisted. And yeah, WebSockets would be good. Or if you would just want to develop apps, you could look up ros.org would be a good place to start. So yeah, that's that.
Hey, how easy or difficult is it to get into ETH?
I just went there for my thesis, so it is quite tough, I guess. Yeah.
Hypothetically, if you were to pitch this to the government tomorrow, what would be the use case that you would probably propose?
If I were to pitch it to the government, that's a very interesting thing. Probably most people wouldn't encourage me pitching it to the government, knowing the track records of general governments right now. But even the US government for that matter, with all the spying and NSA stuff. But yeah, say exploration of the Mariana Trench, or exploration of something, potentially for managing warehouses. I don't know how that applies to the government as such right now, but yeah, that is also one of the challenges. We need to figure out use cases, so potentially we'll get there. It's a very new thing, so the whole concept came up 3 years back. We've made quite a headway, and let's see how it goes from here.
Okay, this thing is on the cloud, and it probably works well within a lab, which you have tested, obviously. Yeah. But have you tried putting this out in the field, as in out in the open, for let's say a sensor network of some sort?
Yes, exactly.
And how does it scale up? How does it communicate with each other at such long distances?
The biggest challenge that's stopping cloud robotics right now is probably your networks. And it also depends on your use case here, right? So if you're doing mapping with RGBD data flowing, then you would need corresponding mobile networks and communication channels to handle that. But if you're doing some sensor networks which are just sending a bunch of parameters and temperature and other sensor data, it should work so long as the networks work. What is happening today is a lot of players are actually getting into the field, really large players. Telecom Italia is getting into it. There's Eugen Robotics, there's Samsung, there is Japan Telecom and telecom companies in Korea that are getting into it with Eugen Robotics over there, so that's interesting. Let's see how that goes.
One last question is, have you tried using it on a swarm? How big a swarm?
So far we've gone 8 robots, but what we were doing was mapping again, and mapping is extremely intensive compared to basic stuff. Potentially it should work for swarm robots. There's no good reason why it shouldn't. Also depends on your latencies. So.
Maybe amusing question. Have you seen the movie Surrogates?
Surrogate.
Yeah, robots walking the earth and being controlled long
distance. I don't think I've seen that movie.
Okay, should watch it. So, the idea is that.
Yeah, I wouldn't be bothered by Hollywood movies.
I know.
Really
do you see? You seem to be.
I mean, when you came up with GPS and Street View, we had Enemy of the State coming out. So. Yeah, there is potential to do whatever you wanted, but to be really frank, there isn't a robot that I know of right now that can hunt you down and slit your throat. Don't worry about it. There's no battery technology or mechanics powerful enough for that so far. I mean, there is a robot that runs at the speed of a cheetah, but it's tied up in a tank in a lab in MIT. So.
And so many companies investing in this thing, like you were talking, right? Eugene Robotics and all.
Yeah.
But may not be science fiction for a long time, I suppose. All these things.
Yeah, let's see. So, again, I said it boils down to how you want to use it. Everything could be good or bad, right?
Thanks.
So, it's up to you.
Do you have more questions?
Any more questions? No? Thank you, guys. See you.